Hello everyone, limits and differential equations, or differential calculus, sorry. Day number 11, part 2 of LHopitals Rule. Today we're going to talk about the following indeterminate forms: infinity to the 0, 0 to the infinity, and 1 to the infinity. We're going to manipulate all of these forms into LHopitals Rule form, either 0 over 0 or infinity over infinity, and then use some advanced techniques in order to solve. So let's get started. Okay, so just a reminder with regards to LHopitals Rule, if the limit as x approaches a of f of x over g of x is equal to either 0 over 0 or plus or minus infinity over infinity, and the limit as f prime of x over g prime of x exists, then the limit of f of x over g of x as x goes to a is equal to the limit as x approaches a of the derivative of both of those functions. Now let's look at an example here of the indeterminate form is infinity to the 0. And I believe I have this actually written wrong. That should be as x goes to infinity. So as x goes to infinity, clearly x would go to infinity and 1 over x would go to 0. So I've got this form infinity to the 0. Now I have no way of manipulating this, at this point at least, into LHopitals Rule form, which would be either infinity over infinity or 0 over 0. However, I'm going to rewrite the limit as a y value. So really, the limit is y. That is the value to which this limit is approaching. Now, what I'm going to do is I'm going to isolate this 1 over x using logarithms. Right? I'm going to take the natural log of both sides. Okay. Now, what I get is the natural log of y, and on the inside, I'm actually going to do a little bit of manipulation and use some rules of limits. The natural log of the limit is the same as the limit of the natural log. Now, the power of 1 over x, which was here, right, can be brought down in front, right? So they can be brought down in front as a coefficient using this law of logarithms. Okay, now, what would this form be? If I just look at the right side, as x goes to infinity, 1 over x would go to 0, natural log would go to infinity. Now I have the form 0 times infinity, which is pretty close to what I want. Okay, so the natural log of the value that this will approach is equal to the limit as x approaches infinity of the natural log of x, instead of times 1 over x, would be divided by x. Now you can see, based on this, that the limit as x approaches infinity of ln of x clearly would equal infinity, and the limit as x approaches infinity of x would equal infinity. Therefore, I will have a form that will fit the rule for L'Hopital. Okay, so what I'm going to do then is, by L'Hopital's rule, then the ln of y, again, y is the output that we're seeking, all right? That is the value of this limit. Okay, should be equal to the limit as x approaches infinity of the derivative of ln of x, which is 1 over x, over the derivative of x, which is 1. Now, if I plug in infinity here, or do a direct substitution, we can see that this would head toward 0, right? 1 over x as x goes to infinity would go to 0. Therefore, since ln of y equals 0, then y would equal e to the 0. Therefore, y would have to equal 1. Thus, the limit as x goes to infinity of x to the 1 over x equals 1. Pretty cool that infinity to the 0 is 1. Not everything to the 0 power is 1. Not every form infinity to the 0 will equal 1, but this one does. Okay, let's look at the next example. Okay, so let's look at the indeterminate form 0 over 0. So as you can see, the limit as x approaches 0 of sine x would be 0, and x would also be 0. Now in an effort similar to the first example, we're going to take the natural log of both sides, where y is the value we're seeking, using properties of limits. I'm going to take the natural log of the sine of x to the x power, bringing the x down in front. So the natural log of y is equal to the limit as x approaches 0 of the natural log of sine x over 1 over x. Okay, now the limit, we want to make sure we have this in a L'Hopital friendly form. The limit is as x approaches 0 of the natural log of sine x would be the natural log of 0, because the sine of 0 is 0. Well, that's going to head to negative infinity. And the limit as x approaches 0 of 1 over x, and I really should do from the right here, would also be negative infinity. What I'll do is, yeah, that'll be fine, right? Okay, so now I can use L'Hopital's rule, and what I'm going to see is that the natural log of y is equal to the limit as x approaches 0 of the derivatives individually. So the natural log of sine x, its derivative is 1 over sine x times the derivative of sine x, which is cosine x. So I get cosine of x over sine of x over the derivative of 1 over x, which is negative 1 over x squared. All right, so I've got this thing. Now I can do some manipulation with this. What I would do is probably multiply by the reciprocal of the denominator. So the natural log of y is equal to the limit as x approaches 0 of, and I'm going to split this up a little bit, cosine of x over sine of x times negative x times x. And the reason why I'm doing that, you'll see why here in just a second, is because I'm noticing something that I might be able to use here. Notice that limit. We know that limit. It's a special one for us. So I'm taking the limit as x approaches 0 of x over sine x times negative x times cosine x. All right, so what I know, based on my previous knowledge and some laws of limits, is that this will be equal to the limit as x approaches 0 of x over sine x times the limit as x approaches 0 of negative x cosine x. All right, so the natural log of y, I know that this limit is equal to 1, special limit, times, and I know this limit comes out to be 0 times 0. So just so happens that the natural log of y ends up equaling 0, which means that e to the 0 equals y, which means that y equals 1. Therefore, all the way back to the beginning, the limit as x approaches 0 of sine of x to the x power equals 1. Pretty cool. Make sure you're following notation, and that you follow it just like I did. Stating L'Hopital when you use it. If you have to use it more than once, make sure you do that. Okay, let's move on to the next example. Okay, let's look at the third form, 1 to the infinity. All right, it looks like the inner expression, 1 plus 1 over x, right, as x goes to infinity, this will go to 0, 1 over x. So it'll be 1 plus 0, which would be 1. And x, of course, would go to infinity as it goes to infinity. Using similar methods, then y, actually the natural log of y, we'll just skip right to it, will equal the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x power. Okay, now I'm going to bring that x down in front using rules of logarithms, excuse me. So the natural log of y would equal the limit as x approaches infinity of the natural log of 1 plus 1 over x over, I'm just going to anticipate, 1 over x. All right, so let's look at the current form. So the limit as x goes to infinity of the ln of 1 plus 1 over x. As x goes to infinity, that'll go to the natural log of 1, which is 0. And the limit as x approaches infinity of 1 over x also goes to 0. So I've got the form 0 over 0 now, which means I can use L'Hopital's rule. So by L'Hopital, ln of y will equal the limit as x approaches infinity of the derivative of the top, which is 1 over 1 plus 1 over x, times the derivative of the inside, right, which the derivative of 1 plus 1 over x is negative 1 over x squared. Okay, that's the numerator, its derivative. The derivative of the denominator is going to be the derivative of 1 over 1 plus, or excuse me, 1 over x, which is negative 1 over x squared. Okay, so you can see what's going to happen here. These two are going to reduce. So the ln of y is going to be the limit as x approaches infinity of 1 over 1 plus 1 over x. Well, what will happen here is if we dissect this, if I plug in an infinity, this will go to 0. So I'll get 1 over 1 plus 0, which is 1. So I'm getting that the natural log of y is equal to 1, which means that y equals e to the 1, which means that y equals e. This is really, really cool and actually very foundational for very important topics such as population growth and all that good stuff. But this limit actually equals e. It's awesome. Okay, now I'm not going to dive through it or go into it too much. But if you took the limit as x approaches infinity of 1 plus k over x to the x power, you will actually get e to the k. You'll get e to the k. Just like I did previously, I got e to the 1. You will get e to the k. All right, so why is that important? Here's the application of that. Let's look at this example down here. Recall that this is the formula used for compound interest, right? It could be in the form of money, it could be in the form of bacteria, population, whatever. Where this is the amount, this is the starting point or principal. So this is the amount after t years, I think it is, or t units of time. Okay, this is your rate. It could be an increase or a decrease. This is your number of times compounded. Number of times compounded. Okay, and then same thing, number of times compounded and number of years or units of time. So if I took the limit as n approached infinity of 1 plus r over n to the nth power, what would I get? Well, it's very similar to what we just did up here. We would get e to the r, right? We would get e to the r. It follows exact same limit methods as we got up here in number 4 and in number 3. Therefore, as we increase the number of times that either a population or a bank account is compounded to the point where it's compounded continuously, so we're sending n to infinity, then the amount or the population or whatever it might be ends up equaling p. Now this whole piece here ends up being e to the r all to the t power, right? All to the t power. So that's where we come up with PERT. That's where continuous compounded interest comes from, or compounded whatever. It's a really cool application, and that's where E comes from. It is Euler's number. It's built from that concept. So, all right, that's it for today's lesson. You'll have plenty of examples where you can use L'Hopital's rule in these indeterminate forms, and maybe even a bonus one here or there. All right, have a great day. We'll see you in the next video.